Well, this right here becomes a big problem. This is not ideal. This is exactly what you do not want. No good. That's terrible. I think they call that being fired, but we'll see.
Let's see what's going on over at Horn Academy today. Hey, what's going on at Horn Academy today?
Hey, we're working on some groove geos.
Nice. Mind if I take a look?
Absolutely. Come on in, take a peek.
Sweet.
So what I want to do is show you some ideal cuts and some not so ideal cuts. So if you're struggling with some cutting parameters, it might help you out. So we are running at 120 meters a minute and our feed rate is 0.12 millimeters of rev. So I'm going to bring these numbers down. It's going to be not ideal for our 4140 material, and we should probably get some stringy chips and then we'll correct those. Just making sure I do the correct things. I forgot to mention something. So this specific insert that we're showing, this is our A geometry.
A geometry. Cool.
We only do the best tools here at Horn USA. Macho tools like Macho Man Randy Savage. We're almost there. All right.
Look at that long stringy chip. It's just rope.
So with our feed rate being way too slow, this is kind of what you're going to get into. Basically, we're not driving the insert hard enough in order to activate the chip breaker. This is not ideal. This is going to get stuck around your tooling, around your workpiece, or your chip conveyor. Also, if you wrap your workpiece and it comes back and recuts, you could break your insert. What I want to do now is speed this back up and see if we can get a more ideal situation of cut. So what we're going to do now is we're going to speed this up to 0.1 millimeter per rev, or about 4 thousandths per rev. This should give us a better cut, but still probably not quite ideal. Let's see what kind of results we get. You can kind of see a little bit of braking going on. The chips are a little bit tighter than they were before, but that's still not an ideal chip. Same problems. You're gonna run into tool wrapping, workpiece wrapping, just all around not a good situation. We'll go back in here and speed this thing up some more and see if we can create a more ideal situation. I'm gonna speed us up to 140 meters a minute, and I'm gonna go to 0.14 millimeters per rev. Let me break that down into, I have to calculate it because I don't have it in my head. I don't know anything about tools. So that's really close to 440 surface feet. And then the 0.14 is gonna be closer to about 5 thou 6/10 per rev. We'll try it again and see what the results are. All right, here we go. One of the things that I really want you to notice is how much tighter the chip looks. Even though this is still not perfectly ideal, what you can see is how our string has become tighter. That tighter wind represents that your chip breaker is activating much better. So this is getting it to be a tighter spiral. So this means that our chip breaker is getting closer to activating the way that it should to roll the chip straight over to begin our actual breaking and cutting. And this thing went everywhere. This is exactly what you do not want right here. You got a long stringy chip wrapping around our parts. It's around some of our fixtures in the machine. All around, no good. I'm gonna have to actually cut this out.
So even though you have a crazy long stringy chip like this, you can tell that you're getting closer to your ideal settings, your ideal feeds and speeds, because they're getting closer together. Is that what you're saying?
Right, you're getting a tighter spiral. And this right here, as you can see, getting tight, that right there in particular is almost about to break. So we're getting very close to what I would call ideal condition for this material. So we'll speed them up again.
What what increments are you increasing by every time?
I'm usually going about 20 meters a minute, and then about usually 0.02 or about 1 thou millimeters per rev. You really want to do it kind of slow. Most of the time, I want to increase one thing at a time. Note any changes in that effect, and then go from there. I usually try not to do 2 changes at once, because I want to know exactly what change created the difference. Tests like this is what we like to really show in our academy as well, because on the production floor, you don't always get this opportunity. You know, we can do different geometries, we can do different materials, and then we can, you know, test these parameters, and we can find higher and lower, more and less tool life, things like that. So we get a better opportunity to kind of play with the parameters versus just, well, this worked once and then stick with it. Kind of a unique thing that we get to do. So basically, I'm gonna increase the millimeter per rev by 20. So we're at 0.16, and we're gonna see if this is enough to get this chip to break. All right, so faster yet as we try to find the correct parameter for this material. This is a 4140 steel and it's annealed state.
See, we're getting a big chip. It's a bit shorter than last time though.
Correct. So let's try it again with just adding coolant and see if that makes the difference.
How does adding coolant affect the length of your chips?
As a chip becomes hot, it can become malleable. So it can roll instead of breaking. That's kind of the main thing.
When the chip cools down, it becomes more rigid, it's more likely to break.
Correct. At least I hope that's right.
You can tell we're throwing smaller chips.
So just by adding coolant, the material becomes less malleable, and now we're starting to break chips. So we're getting much closer to ideal, but I still think we can do better. Close to a 2-inch chip, but I think we can get it better than that. One thing I do want to note is I didn't hear any growling or anything that sounded bad, so I feel like we can keep pushing our parameters ahead without any damage to the insert or premature tool wear. So that's what we'll do. We'll try to speed them on up. Go on up to 0.18 now. So 0.18 millimeters of rev at 140 of our constant cutting feed, which was about 390 surface feet. So right off the bat, I'm seeing what I want to see. Something like this is really what we're after. This is not going to clog your machine. This is not going to get your conveyor messed up. It's not going to tool wrap. This is ideal. So we are all over what I would call the correct parameter. We can tweak it in just a little bit because we're still getting some of these, but overall I would call this acceptable. Something like this is not going to wrap up around your tool or your part. So let's go to 0.2 at 140, accept that. So once again, we're going 0.02 millimeters per rev deeper, or about 1 thou, or increase in our feed. So I finally saw what I wanted to see. So what you can see here is everything is breaking pretty much the way that I would expect it to. Right now we're at 140 meters a minute at 0.2 millimeters per rev. And this seems to be the sweet spot for this particular material. We're creating a nice small chip that's not going to create you any kind of manufacturing problems. And you can also kind of take a look and see that our part itself has a pretty nice finish. I'm going to finish cleaning up this blank, and we'll see you guys next time.
So it's crazy to me that we can use the same tool, the same machine, the same material, and we can get radically different results with our chips. Tell me a bit more about how that happens, Jeremy.
So what's going on here basically is we're starting with a low feed rate of basically 0.8 millimeters per rev. That's also wrong. Holy cow.
Big
chip right
there. Big number.
That sounds professional. So we started at about 80 microns per rev and we ended up at 200 microns per rev. And you can see the huge difference from the starting point to the ending point. Essentially what's going on is we're not feeding the insert hard enough to roll the chips to make them break. So we went up 20 at a time to kind of see where our variances were. We found that about 40 microns is where it changes greatly. So 80 was our starting point. We had just a huge mess of chips here. Definitely do not want this in your machine. And then we moved on up to our 120 millimeters per rev. And we're starting to get some tighter pattern here, but it's still not breaking. Definitely not ideal here as well.
And that's due to the higher speed causing the chip breaker. You can tell that that's starting to engage a little bit more just because of that tighter pattern.
Absolutely, absolutely. And really this tight pattern is what you're looking for right before the chip breaker really engages and starts to work. Specifically, if you look kind of in this area, how much tighter this little section is here than say the bottom half of this.
So that's a great way to tell that your chip breaker is on the right track.
Absolutely. So up 40 more microns to 160 microns per rev. What we're looking at here is we're finally getting breakages. The pattern of the spiral is still about the same. However, that breakage is going to prevent tool wraps, part wraps, or any kind of conveyor problems. We went on up to our 200 microns a rev. Here we got some small chips. This is really what you're kind of looking for as far as like not being able to wrap your tool or get stuck in your machine, things like that. Personally, I think I would probably stick around this range here, maybe somewhere right in between. You can see a little bit of discoloration here. That extra heat may cause a little bit of tool life issues. So you want to kind of keep maybe somewhere between these two would be perfectly ideal, but we're definitely getting right on track around the 160 microns per rev.
So how can you tell that there's a bit of extra heat generated in those smaller chips?
Usually on the color. So if you look, you can kind of see the edges also look almost serrated, I guess would be a good word. You have that extra heat. So you have different color plus serrations of the chips.
And that can negatively affect your tool life, yeah?
Absolutely. Just extra heat would mean tool life can go down. How drastically can depend on the material, but there will be a difference.